Well, as I've already mentioned, my name is José Selvi, and I'm from here in Valencia. I've been working in cybersecurity for many, many years, and working with multinational companies for the last few years. I'm in NCC Group, which is a British company originally, and I'm going to talk a little bit about how I started in the world of massive learning. And this has to basically, I work in penetration testing. It's looking for faults, breaking things, and so on. So around 10 years ago, I started with machine learning because I was doing my doctorate, my PhD at the time. And this was one of the subjects that came up and one of the areas that I liked the best. So I'm going to talk a little bit, give you a little bit of an introduction to the matter of machine learning, in case you don't know much about it. It'll be quite simple, not too much detail, and then we'll look into a couple of examples of things that have been resolved over the last few years using machine learning. At the beginning, I'll talk about one from the beginning, from around 10 years ago, and I'll talk about what things I did, the errors that I made, and the lessons that I learned. Sometimes in talks that I've seen, people go to the actual final solution and not about the process, and not talking about, oh, I tried this and it didn't work, I tried this and it didn't work. And I think that actual process is very important, and that's part of the objective of this talk this morning. So things that I've learned over the years, a few tricks, a few pieces of advice, so that at some point, if you come across the same kind of issue in the future, then you have some indications of where to go with that. I'm going to give you a couple of cases, as I mentioned, introduce a couple of cases. And when we get into the details, I'll let you know a bit more about that. So also some lessons learned over time, and then we'll have the questions at the end. So this question of machine learning, how many of you are familiar with machine learning? A few people here, yeah. Basically, machine learning is a series of techniques that we use in order to try and make a machine learn. That is, you have a model with which you work, and you model a series of entries, and then the system goes into questions of classification, and it is able to automatically classify different inputs based on what you've told the machine previously. There are a few people working in this field, and if in machine learning there are a few people, and in cybersecurity there are a few people who are interested in this field. In actual fact, I liked something that somebody said to me a few years ago. Somebody said that if you've got the skills for cybersecurity and the skills for machine learning, you're kind of like a unicorn. So data science and machine learning has had a big impulse since we've had bigger machines, because we can process much more data now. The machines we had previously did work, but there were issues that we had because we didn't have the power, the ability at the time, and now computers do have that ability. This has grown immensely. In Silicon Valley, they are being used for the areas that they need, and now it's extending everywhere. So in terms of cybersecurity, it hasn't been used for so many years. In fact, I think in terms of cybersecurity companies, I would say it's in the antivirus field that companies are using this the best. So there are continually more and more variants of different viruses and different types of malware. And so it's impossible for companies to have a group of people analyzing that all the time, because the scale of the malware that is being generated and everything that needs to be analyzed is impossible with a team of people. So the kinds of companies in cybersecurity that have invested most and best are the ones that have done most in investing in this field.
Otros de los tipos de empresa que,
or other areas, other fields that where this has many benefits is in the area of the SOCs, because there were a number of alerts and some rules that would give you a number of alerts, and manually people would eliminate different alerts, different alarms, and say, oh, this is an attack, this is not. So let's say that was a 1,000-person connecting a day. Nowadays it's millions of people. So at that scale, it's impossible to do that task manually to see if there was really an attack or not. So this is one of the most direct uses that we can find in the field of cybersecurity. But it can also be used in many, many more. I've brought along an example today, because mostly it is being used for defensive purposes, for detecting malware, but it's also being used in other areas for more offensive matters. This is one example that came up in DEF CON. It's a conference that's done in Las Vegas, and there's a competition, and there are groups of people who attempt to work amongst themselves, and they have to defend a number of servers. And they have to detect their own vulnerabilities and stop the other groups attacking them and exploiting them. And they have to do the same with the other groups. So the more servers that you win, the more points you win. So there was a challenge that was set up within this area, and this was a few years ago now. And there was a similar competition, and this was done by machines in this particular case. So the machines were looking for the failures and exploiting them and setting up their patches and so on. So there were people that had designed the different systems, and they were the one that arranging the competition. It was the machine that was actually involved in the competition, not people. So over time, I've seen that machine learning has become a buzzword. Everybody is talking about machine learning, so it's everywhere now. So if a product doesn't have next generation and it doesn't have machine learning, then it's worth nothing. We will also see a little bit later on that machine has a great deal of power, but it's not useful for everything. These are some actual sentences that I've come across talking to people. And we're talking about, let's put rules for machine learning detection in, and the response to this would be, well, you don't have to stick any rules in machine learning. The machine has to tell you what the rules are. If you give the machine the rules, then it's not learning. It's doing what you've told it to do. Oh, or the projects say, oh, this has got machine learning, but in fact, the machine learning that it's got doesn't work at all. And it's just given a different weight, but actually the result is the hourring that they've put in. They say that it's machine learning, but it's not actually being put into use. Or in some cases, just for using the point of using machine learning, they just use just a few characters. And actually, the power of machine learning is taking a lot of characteristics, and that's the power and the potential of machine learning. And that's something that we can't process. If there are just a few parameters, then we can set up the rule for ourselves. We don't need a machine to do that for us. During this time, when I've seen these few things, I've been a little bit suspicious of that. People say, oh, this has a machine learning, but in fact, it's not actually being used that well.
Entonces, yo os voy a hacer una explicación porque, claro, ni es esto, ni tampoco es que sea que haya que hacer una invocación, haya que...
So I'm just going to give you a little bit of an explanation of this. And I'm going to give you an example to show you how machine learning works in the industry, and then we'll continue. So I just chose a person at random. So you do know who this person is? Perhaps you do, yes, I should imagine. How does our brain work? I show you these photos, and you've seen images of this person many, many times. So your brain is already familiar with him, and it's got an idea of who this person is. What this person is like. So the world of Plato and the world of intelligence is about perception. We perceive the world in images, and we create an idea in our brain of who this person is. And once we have that idea, when we get new images of that person, we apply that idea that we have and to see if it fits or not. So is this the same person that I showed you before? No, it isn't. You know it isn't because it doesn't fit the model that you've got in your brain. Is this the same person? Well, kind of looks similar, but you know it's the same person because your brain doesn't always just retain the images. It's also about, it's not just about memorizing things that you see. It's about using that information. I'm not quite sure how to explain it to you, but it's about taking new data and using that data and saying this is similar. So machine learning, in fact, is all about using this model that we have in the middle here, this function. And it says, does this belong to this or not? And here we have the same model in a little bit more of a formal manner. We have different types of models here. And when are they used? These are the models that we have to construct the idea of a piece of data. So based on the data that we're giving, the process for machine learning is to extract characteristics and process the data. We'll see some cases now and cases in which I've made mistakes. So the data has to be prepared for the model that we're going to use. And then we use the model. In most models, what we do is we obtain a candidate model. It's calculated how good or bad that is, and modifications are made until the model adapts well to the data that we have. This is a little example of the ways in which this can be done. So we try to get a model that would adjust to the data that you have on the right. And if the model is going to be a line, it's got a couple of parameters. We set them in at random, and we calculate the error using that model, which is rather big at first. And then we go adjusting the parameters so that with every adjustment, the model that we end up is better than the last one until it's good enough. Or after several tries, we haven't improved much, then we stop. So we have a line in this particular case which adjusts to the data that we have. We don't need all the data, we don't need all the photos of a person in our mind in order to know who that person is. In machine learning, there are two different types. On the right, it's a regression. So it's a model that basically adjusts to some data. It's a prediction of data. And the other one is what we find in cybersecurity, and it's a classification. It's all about having data of two different kinds, and I want to find a way of the system saying, well, this is of one type, and this is of another type. This is malware, and this is not. This is an attack, and this is not. So let's go on to the first example. This is from 10 years ago. But I'm going to tell you all about the different steps. If you know a little bit about machine learning, then you'll see it. And you'll see that it's not going to work, and in fact it didn't, yes, but you'll see how it improved in the end. This was a friend, basically, that gave me data from the company I was working in that had an intrusion. They'd had 7 months of classified alerts, and there were 120,000 false attacks, that weren't real attacks, and 700 real attacks. This is quite standard in these detection systems. At the end of the day, the rules attempt to detect something that is not a real attack than to not detect a real attack. So this is more or less the data, the piece of data that I had. This is a text from the alert system, from the intrusion alert system. And it would detect certain types of attacks. So I removed some of the data that probably would not apply. And I ended up with the textual description, the IP address and port, the time, and that was it. And I wanted to use that to try and detect when an attack was repeated on many occasions and it was a false attack, if there would be certain patterns, if it was coming from a certain IP, if it was coming at a certain time of day, and to find patterns in order to determine which were the false positives and to determine which were the real attacks. So this was more or less what I had. I put in the date and the IP, I put it in pieces, and the classification, which was 01, whether it was an attack or not. So I used a decision tree. The name says what it does, but here we have some of the characteristics of a decision tree. We have all of these here. So which of these characteristics in this particular case would help me to divide the tree up into different branches? If I could divide the tree up into different branches, then that would help me to take a decision, and it would help me to set priorities. It was built in this way. A characteristic was taken, and you take a decision based on that characteristic, and based on the rest, well, you build up the tree in this manner. Something that I also did was to add in the false negatives. You calculate the error. So depending on when your problem is, it might be so bad to, in this particular case, detect an attack that was not a real attack than to not detect an attack that is a real attack. So I wanted to remove the false negatives, but I didn't want to get rid of any real attacks. So when you calculate the cost of how good or bad a model is, if the real attacks that you've got rid of because you thought they were false, that's very, very bad, and that determines the cost.
Now, so once you have the data and you know which model you're going to use and everything, something that is really important is how are you going to deal with that data. It's common to just take all the data, train the model, and then test it with the same data. But that is really useless because in the end, if you test the model with data that you have trained it with, then it will work, but it doesn't have necessarily to work well with data it has never seen. So these are the two typical ways we use. One is to divide the data, one to train and the other part to test. And the one here on the right, which basically what it does is exactly the same sort of operation, but it changes the little bit that it uses to test. So in the end, it trains with all the data and then it tests with all the data. So it's like having a little window that you move along. So this is why it's most widely used in academia, for example. And why is it important? Because there is a big issue in machine learning, which is of overfitting, which basically happens when your model does not learn, but only memorize. So you train the model with certain data, and it's so used to that data, and it's so adjusted to that data that everything that doesn't work with that, and you can see the good learning would be this curve, but if it has overfitting, then it will have weird things and will start memorizing. So what happens when it memorizes? That when they give you something that you have never seen before, you do it wrong because you haven't understood how it works. You have only memorized. So basically, the way I do it is from the data set I have, I divide it in two. So one, I have my work data set on the one hand, and on the other hand, the test data set. And my work data set, I further divide it between training data set and validation data set. So I train the models with training data set. Of all those models I have trained, I choose with the validation data set the model that has worked best. And then in order to know how good it really is, then I use the test data set. So if you actually fall on overfitting, you will see that your model is very good here, but it's very bad there. So when that happens, it's because you have had overfitting. Your model is overfitting. It's memorizing, not understanding. And that's not what we want. Right, now, this is how what my tree looked like, and there's some trimming techniques to make it smaller, and this is the way it looks more or less. But when I tried it, when I tested it, it didn't work properly. And why? Because first of all, it made weird decisions. The best thing about decision trees versus other models is that it's very easy to see the decisions it's making. You look at the tree and you know exactly whether it's making nonsense decisions. For example, this model was making a decision to classify false positives, taking into account the last 4 little bits of the IP. And that doesn't make sense because 2 IP that share the last little bit is only by chance, but they're not related to each other. Now, there were also weird decisions when the inputs were very different to the training data set, because with the decision tree, if with specific data you've only obtained one data and that was a false positive, then you might get another bit of data, and in that bit of the tree that's been divided by the actual tree, it might be very far away, but the way in which the tree has divided space, it falls into the same classification, so it didn't work properly. Another issue that we had that has nothing to do with decision tree. It's lack of normalization. I just took the data, passed it onto the tree, and that usually brings issues. And remember that we were talking about 100,000 false IDs versus 700 alerts, and that is very unbalanced. So with unbalanced data types, then we find, or data sets, and we find issues. But that is very common in cybersecurity, having very unbalanced data sets, because we have many false positives, not many attacks, and although we have loads of malware, there's also loads of binaries which aren't good and are being generated. So what I did was, right, I'm going to think about other fields in which these issues have been solved. And so I thought about nuclear plants. How much data do you think we have from nuclear plants? Who says many? Who says little? Few. Few, right? Because nuclear plants do not explode very often, thankfully. So what do they do in order to know when the nuclear plant is going to have a failure? Well, what they do is, because they do not have data of when it fails, but they do have data of when it works properly, what they do is they use one-class models. So, as the name says, they only have one class of models. So the ones that we do not have data about, we ignore, and so we only modelize those data that we know. And in this case, is everything that works. So everything that's not that, then I'm going to say it's bad. It's going to be the other type. And that's why I did. So I got rid of real attacks, not really got rid of them, but I just put them on the test data set to see how they were classified, but I didn't use them for the training. And so I chose a couple of models to try. One was a support vector machine, which is basically a model that tries to find a hyperplan, which is a plan in n dimensions, and separates the two different types of data that you are trying to classify. But of course, right now, I didn't have two types of data. So what I did was to use variation that uses a hypersphere. So the hypersphere, what it does is I have the formula, and I'm going to minimize the radius. So I'm going to find the hypersphere for all my data with a minimum radius, because obviously I could use a bigger one, but what I want to do is to adjust it. And everything that's out of that hypersphere, for me, everything that's inside is the false positives, the things that I know that are false positives, and everything that's outside it will be real attacks. And then there was a little trick that I'm going to mention, because you will see it later, is that sometimes in the hyperplan, you will see sometimes that you cannot separate your data with a plan, with a line, with a hyperplan. What do I do then? Well, what you do is you transform the space. You will see later when I show you data that I'm going to write that I've used kernel transformation. I actually tried several models and transformations, and the one that worked the best was the one I used. But in this case, relating to kernel transformations, you can see properly, you see all the data, you cannot divide them with a plan, but you can transform the space, and then you can start dividing with a plan. So, according to the data you have, you will have to transform the space in one way or another. Now, the other technique that I used, just to show you one which is more traditional, because nowadays they're not even in vogue anymore, but some 10 years ago they were quite trendy. And so what I did is I took this and I compared it with Gaussian's sum. And then mixture of Gaussians. You know how Gaussian works. I have data and I can have it in many dimensions. And what I'm going to do is I'm going to start adding those Gaussians, and I'm going to find a model for that data. If it's a very simple model, then I will only need one, but if it's more complex, I might need 100 or 1,000 of them. But in the end, by doing mixtures of Gaussians, you could actually model the data that you have. And finally, what I did once I already knew that I wanted to use those two models because I was going to use only the false positives, then I wanted to start working a bit more with data because, and this is very important, I realized that preparing the data is where you find the best results. If you invest in doing a proper data engineering, it is more important than finding the right model even. So basically what I did with IPs was to group them so that the model understood that it didn't make sense to only use the last bit. So what I did was use the first and second and third bits, so that it understood that it was some sort of sub-network. And then I did another thing, and I'm going to show an example now. From these three IPs, which ones do you think are more similar? If you were the model and you had to classify these IPs, which one would you say is more similar to each other? First and third? And now, if I show you this, now which ones are more similar? If during an attack, which two you would think are more related? The second one and the third one. And why? Because they come from the same country. But this information we have not fed into the model. If we do not feed this information to the model, then the model will not be able to make decisions based on that. So when we give data or information, when we feed data into the model, we have to extract from that data as much information as we can. And then if the model decides or determines that this is not important, then there are other techniques that we can use in order to get rid of the features that are not important. But if we do not give this in the first place to the model, then the model will never know of its existence. Now, another question, and how about these IPs? Which two you think are more similar? I'm waiting for sort of you to say, show me the flags, right? Well, there you go. Now, seeing the flags, which two you would associate with a similar origin, for example? The ones from Asia. Why? Because geographically they're closed. Well, that is something that we need to take into account as well, because this is knowledge that we have and that we need to model in some way so that the model understands them. Because if we only use them as categorical variables, Spain, Germany, so the country, the model will not have a way of knowing that Spain and Portugal have more closeness than the United States and China, are closer than the United States and China. We know because our brain gets more data. We take the metadata from the information, but the model will not know, so we have to feed it to the model. So if we want for our model to be able to do this, then we have to find the right representation for the data that we're going to use so that the model knows what to do with data. So what I did in this case, for example, was because I didn't really trust geolocalization in terms of cities, but I did trust it in terms of countries. What I did was to get the city in a certain country and get its coordinate. And there are many things which are common, things that are close to each other, but for example in this data representation this is not going to be applicable. But in any case, I decided to try this rather than making it more complex, and it actually worked pretty well. So now this is the example with days, which is very similar. At the end of the day, if you give dates to the model, but you didn't say what day of the week it is, or if it's a bank holiday, you can have a pattern. But if you're not telling your model that today or tomorrow is a bank holiday, then it's not going to be able to find that pattern. You will also see that in the cases that we're going to see, because there's only one class, we had to find a rejection threshold, which is basically taking into account from all the data that I have, how many can be outside of the sphere or of the Gaussians. How many can I have outside? Because if I cannot have even one outside, then these spheres might be too big, or the Gaussians might be too big, and then they might be taking data that do not apply. So I tried different values for this as well to see which one worked better. And what I had in the end was something like what you're seeing on the screen down now. You can see the number of Gaussians here, and then you can see the rejection threshold, its index. So this is, you can see accuracy as well, the amount of successes. So which one do you think is best? Which one would you choose? Anyone? The third one, this one, 98.9. Why? It's more accurate. Yeah, but no, because it is true that it is more accurate, but I have tricked you a little bit because I haven't explained this column, and this is the percentage of false negatives. And you have to always bear in mind when you're studying a problem that you have to keep the problem in mind all the time. Because if I define a model that says, is this an attack, and it always says false, having 120,000 positives and 700 real attacks, then saying always that it's not, I will always get a 99% accuracy. So I am very accurate, but I have to take into account the index, the false negative index, the amount of times that I have not detected a real attack. So in this case, for this problem, that is the data that's important. Accuracy, it's absolutely the same, because in the end, what you want is to really make sure that you do not miss any real attack. But if you filter a 70% of false positives, that is already a good result. You don't need to reach 90-something%. But what's really important is to not lose any of the real attacks. So what we want is taking all this into account, getting the minimum false negatives and the highest accuracy. So the best ones would actually be this one and this one. And this is how it looks like in the end, taking also into account the mixture of Gaussians and the one class. And you will see that accuracy is different here because I use different different data set, and it will always work better with the data set it's been trained with than with others, of course. So what issue did I have with this? Well, a friend lent me the data set, and when I said, well, I'm going to publish this, he said, oh no, because I have been allowed to lend you the data set, but my company will not allow for it to be published. So I took many years looking for companies which would give me data and then let me publish them. So in the end, because it didn't happen, I decided to give up on it and do something else, because you can use this internally. If you have a company, you can use something similar. But for companies to lend you the data set of the attacks they get, so that then you can publish them, which you need, by the way, because otherwise it will not be published, then it is really difficult. So it's something that you can use internally, but not publish. So for me, it was a bit frustrating. Anyway, so we're going now onto the second issue that I saw. This time I approached it in a different way. I said, well, first of all, I'm going to check where I have public data set, and then I'll run the experiment, because I don't want to be disappointed again. So do you know anything about malware analysis? A little bit? Well, just to simplify, you have two ways of looking at what malware does: static and dynamic. Static is equivalent to getting to the car, opening the boot, looking at it, but you cannot start the car. You can do whatever you want, but you cannot start the car. Whereas dynamic means you get into the car, you start it, and you go for a drive with it. These could be the two types of analysis, and depending on which analysis you do, on the way you're approaching it, you will use different kinds of analysis. It's the same with malware. You can look at the binary without executing it, or you can execute it. And I basically focused on DNS traffic, because most of the malware that we have nowadays connects from somewhere or to somewhere in order to do something, and it's usually using domain names. And so they use a technique known as DGA, because before what they did was to use a domain name, and when those domains were detected, then they went onto a blacklist, and so the malware could not connect anymore. So what malware have done is not use domain names anymore, but basically generate domains with a seed, a determinist system that I know, and if you block this malware, then it's going to connect to different domain, which I know of. And so that makes it more difficult, because now malware analysis, when they face malware that uses this technique, they have to get into the algorithm that uses those techniques. They have to locate it so that they can block it and block all of those attempts. So I wanted to try this issue to see if I could detect all these names, because they are weird names, right? At least from a human point of view, you can easily see that this is not a normal domain name.
So I took data from Alexa. It has good data. And then I used information from GitHub. And then I had a number of examples and codes that had been taken from these algorithms, and I generated many different names and families, as many as I needed. There was some work that had been done using this, and I'll explain this a little bit later on. And by somebody whose surname is Daluth, and extracting from that name, there would be a number of different characters, number of digits, and the domain name length, and all different kinds of information from the domain name itself, and then a number of bits of data regarding the traffic, the DNS traffic. And this information that I'm showing here was of use to me, but not the other information, because I had the domain names, but I wasn't capturing all that information. And also there were families that weren't working anymore, so I couldn't obtain that data. So I said, what about using this data that is useful and adding some extra things? Would I be able to achieve such a good classification as this person? Because if a family of malware is no longer being used because I can't obtain that data anymore. So in the end, the amount of data that you have for training the pattern with is reduced. So one of the things I end up with was engrams. So if we have a wind with two elements and you move them along, so you have this name, and you have the FA, and then CE, then BO, and then you would move them along across the windows. Some would be only letters, other would be pairs. So if you look here, then you will see there was variations and mean ratio, and they were using the engrams just as they were. So the number of characteristics that you end up with is absolutely huge. And this makes it impossible to use, or makes it very difficult to use using normal hardware. So that's why I use statistics. And I tried something. And instead of using the full alphabet, I used it in a masked way. So there were just some letters and symbols. So generate a name based on the one above and use the engrams using this transformation. So this retains part of the information, consonant, vowel, and so on. And this information could be useful in the end. And the number of characteristics that are required are much less than what we saw before. I used a random forest for this, the same as Duluth had used. But the characteristics that were used were not the best of all of them, but they were cut into sets, and that's why it's called random, because they're not all the same. And then we have a voting system. So if I have 100 trees and 98 say these are the same, then I'll go with the 98. And this is more or less what I had in terms of results. And using 1, 2, and 3 size engrams. So I was doing this in parts, in this case, 1, 2, 3, and 4. Some were of 2, some were of 3, some were of 4, some were of just 1, and I was getting good results. And to do that, I was using a brute system. And so I just get random data and put them in the random forest, just like the others. And one of the characteristics of random forest is that you can determine the importance of a characteristic. So giving the importance of the data, the red points that you can see here are the random ones. So you can see which bits of the data that you've put into the model are the good ones, which have been useful and which have not. So you can see these here down the bottom are not very useful. They're almost as useful as the random ones that I've put in. But on the other hand, there are some other characteristics that are more important. And so I determined to use the ones that had come out best with the top 25, 20, and 15. So I had 15 characteristics with the 15 that you see here, and I had quite good level of detection with that. So out of the 15, there were 9 of the characteristics that I had put in as additional ones. So what I had added in was useful. So you have a little example of this here, an example of the characteristics for the examples of using a random name. And obviously, as you can see, the results are quite different. So I'd like to show you something now. I'm not going to show you the training session, because it did take about an hour in this particular case, and we don't have an hour here. So, but I have saved the model once it had been trained and used. And I'm going to use this to show you a classification. So have a little think, because I've got a list of names that we can use. So this is what comes up after it's been put into use. And I've got a list here with names that I've invented. Anybody here would like to add something to see what the model comes up with? What's that? Okay, so that's foro coches. Is it .com or .s or .com? Just give me a second. I couldn't find the model at the time. Okay, now we have it. This is what it comes up with once it's being used. This is how it classifies the information. So this is the classification that it comes up with. It's malware, but generated with DGA. I've trained this with DGA, so probably if it's not DGA, then it wouldn't detect it.
Chat.
Let's try chat loons. .at. Is that how you write it?
¿Así?
No, it comes back as clean because I've used DGA algorithms, so that's what it detects. So this doesn't have a strange form to know if a normal name's got malware, then you'd need to do other things to it. So this model has been trained to detect that manner of constructing using an algorithm, so it's not going to come up with that one.
Tenéis por aquí
in my GitHub and in Docker Hub, you've got this information. It's here in a Docker. You can go to Docker pool and you can download that. You've got the data. Oh, I haven't got internet connection. The data is available there, so you can access that. No problem. So let's just go to the lessons learned in the time that we've got left here today. What did I learn? I learned about keeping focused on the problem in hand. You have to focus on the issue, and perhaps the result is that, oh, I only get 70% result. Perhaps 70% result is good for the issue that you have. Perhaps it's better than what you've got now. You have to concentrate on the issue that you're trying to resolve. And secondly, spend time doing feature extraction. If we only extract 2 or 3 little bits and pieces, and we intoxicate it with what we think it should be coming up with, but if we put the blinkers on, it'll only end up giving us what we want it to give us. So we're not making the most of the model. We're not making most of the techniques for the model to tell us and to give us patterns that we are unable to deal with because they've got different characteristics. I love machine learning. It's a very powerful tool, but I don't think it's the solution to everything. But in this particular case, if you only had to use these 4 characteristics, then it will work much better. There's just a few characteristics there, and you can end up with the pattern. So instead of getting into machine learning here, which would not make any sense, we have to know when to use it and when to use it. There are always different solutions, and machine learning is not always the best solution. You need to prepare your data carefully for the model that you're going to use. So you get the country, the coordinates, for example. All of this data helps the model. You have to leave it prepared so the model can use the data correctly and appropriately. Try and keep things simple. In the first example that I gave you, it was more complex than the sum of the Gaussians, although the sum of the Gaussians worked very well. Some people only have a neuronal network and they get the solution straight away. But this can be very complex and they have other types of issues. So maybe other simpler solutions that will give you the result that you're looking for. Don't get frustrated. How many dogs can you see in that picture? About half of them? About 8, 9 and a half, maybe? So what I mean is that don't get frustrated. Okay, so we put in the information before the name's in before, but the name of my company comes up with as a malware result. So there are different layers, and your model doesn't have to solve everything. Don't get angry, even though you don't like the results of the machine learning. Sometimes people get angry with the result that they get, and that's not necessary. So that's everything for today, unless anybody's got a question for me. Thank you all very much.